right, well, on that note, let's go ahead and get started with class. A review over some things we talked about just last lesson, first of all. We looked at things, I think it was a baseball, a brick, and now a pencil that are launched or hurled through space, or in this case just dropped. But still, it went through space, unable to propel itself, and so we call objects that are launched or hurled through space class projectiles. Good. The path that a projectile follows, like the pencil as it slides off the desk and goes down to the floor, that path is called its trajectory. And we said that the path of a projectile, if we ignore air resistance, will be in what shape class? Parabola or part of one. Okay, a parabola or part of one. So I think the term I used was a parabolic trajectory. Now, yesterday we had a brick, much like the pencil, that was knocked off the top of a building. And we also had a baseball being thrown off the top of the building, and perfectly horizontal. And we said, which one, if there's no air resistance, will hit the ground first, Michael? They'll both hit the ground first. Neither will hit the ground first. Either answer is correct. They'll hit the ground at the same time, won't they? If there's no air resistance, right? Because vertically, their motion was the same starting out. Vertically, they had the same displacement. They had to fall. Vertically, they have the same acceleration acting upon them. So therefore, vertically, they will take the same time to hit. And vertically, their final velocities would be the same right before impact. The difference is the baseball lands over there and the brick still lands down there like her pencil. Okay, so the velocity in the x, the movement in the x, is not affected by movement in the y. Those two components can be separated. Let's go back to the top of that tall building now. And so we still have a vertical displacement, or a displacement in the y of 12.5 meters. And this time, instead of throwing a baseball, let's suppose we shoot an arrow horizontally. So we have an arrow being shot horizontally at, let's say, 89 meters per second. Now, truth be told, for an arrow to function well, you really need the air resistance, right? The air resistance keeps it going kind of straight and true. That's what little feather thingies in the back. But we're ignoring air resistance here. And the arrow shot 89 meters per second horizontally. If it's perfectly horizontal, is it being shot up or is it being shot down? Neither. Absolutely not. Perfectly horizontal. So will it go up or will it go down? Down. Even though it's not being shot down, it will go down because of gravity, right? But it starts out horizontal. So initial velocity in the y class is 0 if it's perfectly horizontal. Now initial velocity in the x class is 89 meters per second. We know it will not stay going 0 meters per second vertically because of, as we already said, gravity, which accelerates the arrow down, down, down to the earth. And it goes down at a rate of class 9.80 meters per second squared. Felt like I was reading a children's story for a moment there. All right. I'm a very good reader of children's books. I just want to go on record as saying that, self-proclaimed. All right. I can read Scuffy the Tugboat with great expression. It's a great book, great book. Anyway, what's the acceleration in the x? What speeds up or slows down the arrow class horizontally? None. If there's no air resistance, there's nothing to slow it down, and there's obviously nothing to speed it up once it's in flight. There's no acceleration in the x. So we understand in the y, because there is acceleration, there must be inherently a change in velocity, correct? So I don't know what the final velocity in the y is. But in the x, if there is no acceleration class, I do know the final velocity in the x. 89 meters per second. Got to be the same as it started out if there's no acceleration, correct? Which means, and this is where we went with this last time, as we said, if that's the case, if the final and initial are the same, then we could just say that the average velocity in the x is the 89 meters per second. It's an easier way to think of the horizontal movement. Now, the displacement in the x. I've got all this up here. I've just said, well, I got a displacement in the y. What about a displacement in the x? I don't know. Just like I don't know the final velocity in the y, so we'll put a question mark. There's only one thing missing, class, for both the x and the y, and it's the time. Should I say time in the y and time in the x? No, because remember, time's a scalar. Time's going to be the same regardless. So the question comes, I've got two things I don't know about the y. I've got two things I don't know about the x, correct? What should we solve for first? Always find the y first. I think I have you put that in your notes. Specifically, always use the y to find time. Now, I also want to know the final velocity in the y, but we definitely need to use it to find the time. You might still have, in one of the memories of your calculator, you might still have the final velocity in the y. I don't think I do. Do I still have 3 memories in here? Recall 1? I think that might be it. My recall 1 is 15.65. I think that's actually the final velocity in y. If we didn't have it, Michael, how could we find this final velocity in the y?
Vf squared equals vi squared plus.
That's a square, it just doesn't look like it.
Plus 2ad.
Plus 2ad, good. Now, a word of caution. When doing calculations, be careful not to confuse x pieces with y pieces. You have to keep things within their own components. The only thing that can cross over between the two class is time. Everything else must stay with its own. So you can't say, well, initial velocity is 89. Oh, no, it's not. 89 is in the x. In the y, it's 0. So when we take the square root, we're taking the square root of 2ad, and you should have, Michael, that 15.65 that we still have apparently in the memories of our calculator. I'm going to go and notate. For me, it's still in memory 1. You ladies notate whatever memory it is for you. All right, and then we could use this information then, once we found final velocity, to get the time. That might be in memory 2. I think it is. Since we didn't use these much for pre-cal yesterday, we didn't need our calculators much, so we didn't change anything. Is it still in memory 2 for you? 1.597? All right, Michael, if we didn't still have it in the memory of our calculator, how could I find the time it takes for the arrow's descent to complete?
We can do the average velocity equals d over t.
I could average these two. That could work. I could do it a little easier, though, without...
A equals vf squared.
Ooh.
Or vf minus vi over t.
Yeah, definition of acceleration, and then alternate. That way, I just keep whatever's on your calculator right now, or in memory, whatever, and just divide by the 9.8. It's fewer calculations that way. And you should have the 1.597 seconds. That's still in memory 2 from the brick and from the baseball, because their vertical motions are all the same. Now, again, their horizontal motions are vastly different. The brick had no horizontal motion. The baseball had a good deal of horizontal motion. This arrow is going to have way more still, correct? But their vertical component is identical. Does that make sense? If there's no air resistance, same displacement, same initial velocity, same acceleration, they all have to have the same final velocity and time in the y. Now again, this time travels across the two components because it's the same in both respects. So now if I want to find the displacement in the x, how far from the top of the building, so here's building, here's the little guy sitting there in a chair, okay, and he's got bow and arrow, and he shoots arrow. Okay, does arrow stay, how long does arrow stay perfectly horizontal if there's no air resistance? Now, if there is air resistance, it can stay horizontal longer, can't it? But no air resistance, it's going to begin dropping immediately. Now, it's going to be a minute drop, right? But it's going to begin dropping immediately. And obviously, the faster it goes further, 89 meters every second it's in the air. Well, it's in the air for 1.597 seconds, right? And every second it stays in the air, it continues to go 89 meters per second. How would I find this displacement? Average velocity in the x equals d over t, where I simply multiply the time times the average velocity in the x. Take that memory 2, or what's on your calculator right now, multiply by the 89, and how far from here does the arrow end up landing? Call it? 142.15, blah, blah, blah. I'm thinking we did 2 sig fig. Well, it was 3 in these. It was only 2 here, so rats. We'll have to change it to 2 sig figs and go 140 meters. By the way, that could count for, well, but again, air resistance would have kept it up in the air a little bit longer still too. So about 140 meters from the base of the building is where it landed. Now again, that's not the actual distance the arrow itself traveled, right? That's just the distance from the base of the building. Questions on finding the displacement of the x. But there's one more question, right? And that's, how fast was the arrow actually going? Because although there wasn't any acceleration in the x, there was an acceleration in the y, correct? So the arrow should be going faster when it hits than it did when it was released at the top of the building, yes? So to find the final velocity at impact, remember the arrow was constantly going 89 meters per second this way. But right as it hits the ground, vertically it was going how fast, class? 15.65, blah, 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 meters per second. Memory 1, correct? So when it hit the ground, we could find the resultant final velocity. The real v sub f, not v sub fx or v sub fy, but actual v sub f. Now, not going much faster, is it? What's the magnitude of the resultant to your class? 90.36, blah, blah, blah. So did gravity speed it up much? Nah, not much at all. Also, though, it'll tell us the angle at which it would hit the ground. Again, if there were no air resistance. This angle, which is also this angle, which means with respect to this angle, class, 89 is the adjacent, and the 15.65 is the opposite. And if I want to use the tangent or arctangent, right? Tangent is SOHCAHTOA, tangent is opposite over adjacent. So we're going to take the arctangent of the opposite over adjacent to find that angle. So there's that recall 1 divided by 89. And we take the arctangent. What angle is here, and therefore at what angle to the ground does it strike? 9.97 blah, blah, blah degrees, or rounded off 10 degrees to the ground. So it's not doing a nosedive, is the point. Again, if there's no air resistance. It's just going to come in at that angle. All right, questions on that? Turn over in your books, if you would, to page 109. Turn over to page 109. And I want you to do problem 8 there at your seats. Get a head start on it. And let you work for a couple of minutes, and then I'll start putting up some work on the board so that you can check and make sure you're on the right track. Problem number 8 on page 109. It says if an apple's dropped from an air balloon at 1,350 meters, this is like Sir Isaac Newton on steroids, not content to merely be hit on the head from a tree, he goes up in an air balloon to drop it on somebody else's head and see if gravity still works. 1,350 meters up, an apple is dropped. Find the velocity at which it strikes the earth and find the time it takes for the apple to fall. Make sure you put those things in the memories of your calculator as you find them. You will need them in a moment.
hot-air balloon.
It's artistic. Sir Isaac Newton's the guy in the balloon dropping the apple. And that's Michael sitting in a lawn chair.
Oh, I thought that was
Got a
God.
calculator. Which did you find first, Michael?
I found the final velocity.
I think it's easiest if you do it that way. You could technically find time first if you use the d sub I, or d, excuse me, equals v sub I t plus 1/2 at squared. You can get away with it because the initial velocity is 0, so you could do it that way. I think it's easier just to say that Vf equals the square root of Vi squared plus 2AD. You still benefit from canceling out the V sub I. So, displacement of 1,350 meters, accelerating at 9.8 meters per second squared. How fast is the apple going when it goes clonk on the noggin?
163 rounded meters per second.
Yeah, 162.66. I'll go ahead and put this in my memory 1, but 163 meters per second. That thing's going. An apple, by the way, would not hit terminal velocity for a while anyway, so it's very possible that's a very realistic number even with air resistance because of the apple's aerodynamic shape. Maybe closer to 160, but still going to be pretty close to that. How many have the 163? All right, then we can use that number to find the time. Again, I would alternate in the acceleration equation and take this number divided by the acceleration to find the time it would take to go. And then, of course, whatever sound an apple makes when it strikes someone on the head. A squelching sound, perhaps? I don't know. A splatter as apple juice goes flying and spraying everywhere. Anyway, how much time does it take to go squelch? Audrey? 16.59, blah, blah, blah. Pretty much 16.6 seconds till squelch. And I'm going to put this in memory, too. Did we all get to 16.6 seconds? Questions on this? Now, Sir Isaac Newton would not be so inefficient as to make a hot air balloon trip up there just to drop one apple. He has a backup. And there's also, further down range, there's another lawn chair. It's a big lawn chair with Kendall in it. He decides now that he will take aim, and he will throw his apple perfectly horizontally, knowing that the apple will not stay horizontal, but will rather go like that. Okay? So, if problem number 9, the apple is thrown horizontally. Now, Newton was not a baseball player. He was a mathematician and scientist. Okay? Cut him some slack. His throw was only 22.0 meters per second initial velocity in the x. Now at your seats, I want you to find letter A. With what velocity does it strike? Now it says the Earth. It's Kendall, actually. It just tried to be nice. It didn't know Kendall. What is the final velocity now? And I also want to know how far from Michael is Kendall. That's not in the problem, but I want to know that. How far from Michael is Kendall if it happens to be a perfect throw? Because he did all his calculations because he's Sir Isaac Newton. At your seats. And Audrey's like, and where am I? What is my fate? You're up in the hot air balloon with Sir Isaac Newton. He's going to check you next. I'm just kidding, just kidding. We don't hate Audrey here. Do we, class? We love Audrey, don't we? Yes? Anyway, a little more enthusiasm, gang. Help her out. Right. Oh, you did all of it already? You already did problem 9?
Yeah.
Show off. Audrey's up in hot air balloon like, give me an apple, let me at him. Where's that brick from the last problem? We'll give Kendall a Granny Smith apple, though.
Can I
Make it
have
great.
a pink lady apple with it?
I have had a pink lady apple. A little sour. Not as bad as Granny Smith.
Give Kendall a crab apple.
Not so much. Not so much. I think my favorite are the ambrosia apples. I think they're the perfect blend of crispness and sweetness. So I love the ambrosia apples. Honeycrisp are pretty good also. I don't like mushy apples. I just don't do the mushy. Like red delicious apples, soft, just not so much. Unfortunately, ambrosia and Honeycrisp apples are expensive. All right, if the apple is thrown at 22 meters per second horizontally, that's the initial velocity in the x. What will be the final velocity in the x class? Also 22 meters per second. Therefore, we could say, class, that if the initial and the final are both 22, the average velocity in the x is 22 meters per second. And this is all true because the acceleration, Audrey, is, in the x, x is that way. 0, there's no acceleration in the x. Acceleration y, yes, none in the x. So acceleration in the x, 0 meters per second squared. If that's true, we know right here the final velocity in the y. And we know the final velocity in the x. How would I find the actual final velocity, class? Put them together, right? Take the larger one, which is the y. I would start with that one. Final velocity in the y, 162.66. Take the final velocity in the x, which is a measly 22, and find the actual final velocity. And a little bit faster. What's the final velocity of the apple?
164.
And Kendall's like, it hits me harder than it hits him. Sorry, Kendall, that's the way the apple squelches. All right, cookie crumbles, whatever it is. Also, where on Michael, it clonks him on top of the head, this doesn't quite go straight down on top of Kendall, does it? It's going to strike at a particular angle, theta. Now, normally the theta would be up here, wouldn't it? But we want the angle to the ground, which is this angle. So with respect to the angle at which it hits her, class, this is my opposite. It's not the incoming angle up here, but it's this angle down here with respect to the ground. This becomes the opposite. The 22 becomes the adjacent. So I'd have to take that memory divided by 22 and take the arctangent. And it's not quite coming down at a perfect 90-degree angle, Kendall. It probably hits you instead of the top of the head, kind of like the forehead, like when Goliath got hit by. Anyway, so what is the angle, Kendall? Then it goes squelch.
82.297.
Good, 82.297, blah, blah, blah. Roll round to 82.3 degree incoming angle. So that's the final velocity. It also asked how much time does it take? Well, we already knew how much time it took, class. 16.6 seconds. And then I added on one more thing. How far away from Michael would Kendall have to sit for that throw to perfectly get her in the forehead? Well, how would I find displacement in the x? Take that average velocity equation and just multiply. It's in the air for 16.6 seconds, and every second it goes 22 meters. So Take the time, multiply by 22, and how far away is Kendall?
About 365 meters.
About 365 meters away from Michael. So close to 4 PE fields. That's a good safe distance, except if there's a hot air balloon with apple throwing scientists. All right, questions on problems 8 and 9. Questions on projectiles that either go straight down or go down from a height. Now we understand every time, every problem's been perfectly horizontal, perfectly horizontal, perfectly horizontal, right? We don't usually throw things perfectly horizontal, do we? Oftentimes we'll throw things at an angle. Let's talk now about that aspect of projectile motion. Page 106. And now we talked about these in Algebra 2, so you're already familiar with all the different ways that a parabola can look, all the different widths, if you will, of parabolas. And we'll look at this more in pre-calculus later on in the year as well, Michael and Audrey. But even from Algebra 2, remember we could change the height or the width of the parabola by changing that a value at the beginning. So we could either squish the parabola down, which spread it out, or we could stretch the parabola taller, which made it skinnier. Parabolas can come in a lot of different shapes and so forth, but there's always that perfect symmetry, isn't there, in a parabola. Now, with something coming from a height, we were really only doing half a parabola, weren't we? We're basically starting at the vertex of the parabola and going downward from there. But look at example 7.10. Let's have Audrey read this for us.
When a volleyball player serves, she hits the ball 20.0 meters per second at an angle of 30.0 degrees above the horizontal. How high did the ball rise before it started to fall? If another player caught the ball at the same height it was hit, how long was the ball in the air, and see what was the ball's range horizontal displacement?
All right, so you realize the ball is not going to travel in a straight line, correct? The ball will not do this. But for a split second when the ball is hit, I'm guessing actually probably underhand serve, right? You don't want to underhand serve the horizontal because that'll go either into the net or just under, into, okay? You want to hit it up at an angle, correct? Now its actual trajectory would go something like this. But for a brief moment, it is going perfectly at an angle. This volleyball player is hitting the ball at a 30-degree angle. Let's presume underhand serve, so it's leaving her hand, and somebody on the other team or somebody back there somewhere catches the ball, okay, instead of hitting it back. So anyway, probably a bad idea. Nothing good can happen when you catch the volleyball, okay? It's hit at 20 meters per second at a 30-degree angle. Now question, is the ball being hit forward or is it being hit upward, class?
Yes.
Yes. A little of both, isn't it? Some of that movement, some of that initial velocity will be in the x forward, but some of that initial velocity will be in the y upward. Does that make sense? This is not x or y, it's a little bit of both. And so what we're going to have to do, kind of like we did a couple lessons ago where we took a single vector, split it into its parts, we're going to take this vector and split it into its parts. Now, this 20 meters per second is the hypotenuse. With respect to the angle, my x, class, is the, and my y is the opposite. Kendall, which trig ratio would I need to find the initial velocity in the x? SOHCAHTOA.
Cosine.
Cosine. I'm going to need the cosine of the 30-degree angle. Remember, we can say the cosine of any angle equals adjacent over hypotenuse. Well, in this case, Kendall, we'll say that the cosine of the 30-degree angle is equal to the adjacent v sub I x over the hypotenuse, 20. And all we have to do, if we put this over 1, is cross multiply. How quickly does the ball move forward as it leaves her hand? How much forward movement do we get, class?
17.32.
So it moves forward at a rate of 17.32 blah, blah, blah meters per second. Put that in memory 1. But the ball's not just moving forward toward the net, it's also moving upward to make sure it gets over the net. Very important that it gets over the net. All right, and so let's see here, v sub I y. Well, what trig function do I need to find the initial velocity upward, Michael? Sine. So, katoa, there's the opposite, there's the hypotenuse. We know the sine of any angle is equal to the opposite, that's a weird O, over the hypotenuse. So in this case, Michael, we'll say that the sine of 30 degrees, because that's the angle, is equal to the opposite. V sub I y over the hypotenuse, 20. And again, put it over 1, cross multiply. And how rapidly does the ball start moving upward? 10 meters per second. We don't need a memory for that because it worked out evenly. That's how everything starts. As soon as there's impact, you hear the impact, it shoots forward at 17.32 meters per second, and it's shooting upward at a rate of 10 meters per second. Now here's the question. If there's no air resistance, one of these is going to stay the same. Which one? Forward. If there's no air resistance, the ball's just going to keep going forward at the same rate. So the final velocity in the x is also going to be 17.32 blah, 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 which means, class, we could say that the average velocity in the x is 17.32 blah, blah, blah meters per second. One of these does change, right? Which one, class? The y. There's no way the ball just keeps going every second, another 10 meters up, okay? Right? The ball will rise, but it will start to come back down. Why does the ball stop rising at some point? Gravity. Because gravity pulls the ball downward. The launch was intended to send the ball somewhat upward, but gravity's going downward. So we would say here that gravity's acceleration, class, is negative 9.80 meters per second squared. We didn't have to worry about the negative earlier because we intended the object to go down. Now when the volleyball is hit, although yes, you have the intention it will come down on the other side, the volleyball's actual hit is intended to send the ball upward. And it does, but gravity pulls it back downward. Does that make sense? So that the final velocity in the y, now again, remember when we threw something straight up, we said let's just freeze it at the highest point. This ball is going to travel in a parabolic path. Right here at the highest point, it will momentarily stop going up, correct? It's always moving forward, constantly moving forward. But for a brief moment, it rises, and it rises less, and rises less, and rises less, and right here, at the vertex of the parabola, there is no more rise. And then it begins to come back down, correct? So we would say that at this point, at the vertex, the vertical, the y final velocity, class, is 0 meters per second. If that's the case, if we know the initial, we know the final, and we know the acceleration, I can find a couple of other things about the y. Ignore the x. What else can I find about the y? The displacement in the y. Now, does that matter, Audrey, what the displacement in the y is? We don't want to hit the ceiling, do we? Bad things happen then, right? Because if it bounces back on our side, they get a point. And if it lands on their side, they get a point. We don't want to hit the ceiling on the serve. So we want to make, but it also needs to get high enough to hit the net, right? So we do actually care what the displacement in the y is of this hit at the vertex, at the high point. We also care about the time that it's in the air. The longer it's in the air, the more reaction time the other team has, right? So we also are curious about the time. Now, we don't say time in the y because time is not a vector. It's just a scalar, right? So we can find both of these things. Given all this, I'm going to need a couple equations. What equation might we use to find displacement in the y? If we wanted to start there. Obviously, we can't use time because we don't know it yet. But using the other four, what equation has the other three things in it? By the way, do you see how I keep the y separate from the x? Either in columns or in this case in rows, you keep them separate. Don't try to mix the two together. Okay? Be careful on quizzes and tests. I'm looking for the displacement though, so I need to get the d by itself. What do I do here, Kendall?
You add the vi squared plus negative, and then you divide it into it.
There we go. Now, conveniently, the final velocity is going to end up being a 0, right? At that vertex point. So we can ignore that. Take the v sub I, the 10, well, you can do that in your head, 10 squared. So the numerator is just a negative 100, right? And then now the 2a, 2 times negative 9.8?
Negative 19.6.
So we got to do, oh, negative divided by negative?
Positive.
Cancel and positive. What's 10 divided by 19.6?
35.102.
5.102, blah, blah, blah. So round it off, I'm looking at 2 sig figs. So we'll say
5.1.
5.1 meters. That's how high it goes. Now, that's about 16 feet. Activity center ceiling in the gym is about that 16 to 20 foot range. It's pretty close. We might be hitting the ceiling. Normal gym, you're going to be fine. And we're definitely getting over the net because the net's just north of 2.2 meters high. So we're definitely clearing the net. We probably don't need it to go that high, okay? Admittedly, but that's how high it goes. We also want to know how much time do we have between whop and it finally gets caught over there. Well, what would I use to find time? Hint, I don't want to use the displacement if I don't have to. VI, A, VF, and T.
A equals VF minus VI over T.
Acceleration equation, A equals VF minus VI over T, where once again we alternate, get T equals VF, which is 0 anyway, minus V sub I over A. So we just take the initial velocity, divide it by the A, negative initial velocity, right? So negative 10 divided by negative 9.8. How much time does it take, watch, to get right here at the high point? 1.02, blah, blah, blah. We'll say about 1.0 seconds. That's to the high point, correct? Now we know this, that a parabola is perfectly symmetric. Air resistance will change that, admittedly. And yes, a volleyball player needs air resistance. That's how you put spin on the ball, changes the flight of the ball. You want that spin, you want that air resistance. But if it were in a vacuum, which everyone's technically dead because they can't breathe, but if that's the case, if it takes 1.02 seconds to get here, it's going to take another 1.02 seconds to come back down, correct? So what's the total time the ball's in the air then?
2.04.
2.04, blah, 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 which means, round it off, 2.0 seconds. That's how long the ball's in the air. And the whole time it's in the air, it's going forward at 17.32 meters per second, right? So how do I find from here to here the displacement in the x? Yeah, multiply the velocity times the time. Take your 17.32 that's in memory 1, multiply it by the 2.040, blah, blah, blah. And how far does the ball travel?
34.64. I didn't have the memory.
You don't have the memory.
Yeah, mine was raised too.
Yours was erased too. Yours too, for shame. 35.3, blah, blah, blah. We'll round off to 2 sig figs anyway. We'll say 35, and I think you would have had that regardless, right? Same 35 meters. Now, Audrey, how deep is a volleyball court? Serving line to end line. That's to net is 30 feet, so 60 feet. 60 feet. That's about 106, 107 feet. She's way overshooting this thing. She's hitting it way too hard. And kind of feel like way too high as well, right? Well, what if we just shrunk the angle down a little bit? Like, because you want to hit it hard, don't you? If we shrunk the angle, wouldn't it make sense it wouldn't go as high? It also wouldn't stay in the air as long either, would it? And if it doesn't stay in the air as long, it won't go as far. So we could get it there quicker. We might actually land it in. So let's shrink the angle here. Instead of hitting at a 30-degree angle and getting it that high, let's change our angle, Audrey, to, let's just say, 16 degrees? All right, so let's go with a 16-degree angle. She still hits it just as hard, but it's a 16-degree angle now. Well, that's going to change these numbers, isn't it? So let's find now, what's the new initial velocity in the x? Again, the initial velocity in the x is our adjacent, so we're using the cosine here. What do we got?
19.225.
All right, now notice, it's now going faster forward than it was before. So by shrinking the angle, it's flying at the other team more rapidly. We'll see if this backfires. Make sure you put this in the memory. All right, by the way, if that's the initial velocity of the x, and there's no air resistance, there's nothing to speed it up or slow it down, class, what's the final velocity going to be in the x?
That.
Same thing. And so what's the average velocity in the x? Same thing. Find how fast it goes up. It's not going to go up as quickly, is it? Because we shrunk the angle. So using the sine, since that's the opposite. Ooh, we almost cut that in half. Which cut the angle in half, so it makes sense. 5.512, blah, blah, blah. Put this in memory too. But gravity's still going to decelerate. Gravity's still going to pull it back down at a rate of negative 9.80 meters per second. At the high point, it's still going to come to a stop. Go back to this equation. V sub I squared divided by 2a. And how high does it rise this time? Not nearly as high. In fact, I think we hit the net. Michael?
How do you get it?
Somebody else?
12.2.
Ooh, no. Okay, recap. This is all the y component, right? We're going to say the final squared minus the initial squared divided by 2a is equal to d. Final doesn't really matter. Notice the negative of the a will cancel with this one. So we can just take the v sub I squared, v sub I, which is in the memory, square it, divide it by 2, and divide it by the 9.8. How high does the volleyball rise?
1.5585.
Yeah, it's hitting the net. But let's suppose they lowered the net. What would happen if it didn't hit the net? Okay, theoretically. Well, let's see how long it would stay in the air. Same equation as before, except now this memory 2 is my VI. And we divide it by the 9.8. How long does it take to go up to its highest point, class?
0.5625.
0.56 blah, blah, blah seconds. And, but that's only the time to go up. What comes up must come down. How long is it going to stay in the air total? 1.12 blah, blah, blah seconds. Now, the whole time it's in the air, it's going this fast. Take the time in the air times your memory 1. And how far does the ball go from serve to catch? 21.62 blah, blah, blah meters, about 22 meters. If the person stood about 5 or 6 feet back from the serving line, it might get caught right at the other serving line, but it would have hit the net. Yeah. Tomorrow we'll do this one more time, but we'll increase the angle and see if maybe hitting it higher would make it still land in, and we'll kind of approach it that way. Homework for this evening has nothing to do with the up and down stuff. It's just the downward motion. Excuse me, I think it's just vertical motion. There's not even any horizontal at all. So it's kind of a review of stuff we did in the last chapter. Page 109, do problems 10 and 11. Page 109, do problems 10 and 11. And we'll work on more up and down at a launch angle tomorrow. Page 109, problems 10 and 11. All right, have a wonderful day, and you are dismissed.